Rack-scale computing is making a powerful comeback, reshaping how data centers handle the enormous demands of today's AI-driven world. But here's where it gets controversial. For years, the industry focused on individual servers as the core unit of infrastructure. And now we're being asked to rethink everything at the rack level. Why is this shift happening? And what does it mean for the future of computing? For decades, servers have been the cornerstone of data center design. When deploying applications or workloads, the standard practice has been to allocate a sufficient number of servers to meet the demand. Monitoring systems, power management, and other operational tasks have traditionally been managed at the server level. This approach made sense when workloads were smaller and less complex. However, as artificial intelligence workloads grow exponentially in size and complexity, the traditional server-centric model is showing its limitations. Enter rack-scale computing, a concept that isn't brand new, but is finally gaining traction because it better aligns with the needs of modern, resource-intensive applications. So what exactly is rack-scale computing? Simply put, it's a strategy where the primary unit of IT infrastructure shifts from individual servers to entire racks. Instead of focusing on how many servers are assigned to a workload, the emphasis is on provisioning enough racks, each carefully configured with the right mix of compute power, memory, storage, and networking components to efficiently support the workload. This is a significant departure from conventional thinking. Most data center managers are used to sizing environments based on the number of servers or nodes, like when setting up Kubernetes clusters, rather than considering how many racks are involved. But in a rack-scale model, the total number of servers becomes less important than the number of racks and how each rack is optimized. Why does this matter now? Because AI workloads demand integrated performance that traditional server-based setups struggle to deliver. For example, racks capable of handling up to 1 megawatt MW of power can provide a level of performance and resource density that individual servers simply can't match. At first glance, adopting rack-scale computing might seem counterintuitive. After all, racks can vary widely in size and capacity, so why treat them as the fundamental building blocks? The answer lies in the variability of servers themselves. Servers differ greatly in their computing power, making them an inconsistent metric for capacity. Racks, when designed thoughtfully, offer a more flexible and scalable way to manage infrastructure. Rack-scale computing brings several key advantages. It supports large-scale workloads more effectively. Many modern applications require multiple servers working in concert, and dedicating an entire rack to such workloads ensures they have the resources they need. It enhances reliability. While individual servers can fail, it's rare for an entire rack to go offline. This means workloads running on rack-scale infrastructure tend to be more resilient. It allows for tailored optimization. By focusing on the rack as a unit, data centers can customize hardware configurations to match specific workload requirements. For instance, a workload with heavy network traffic can be assigned to a rack equipped with advanced networking switches or multiple switches to handle the load efficiently. Interestingly, rack-scale computing isn't a brand new idea. Microsoft was advocating for it as early as 2013, and companies like Intel explored it within composable infrastructure frameworks years ago. Yet, despite these early efforts, the industry never fully embraced racks as the primary infrastructure unit. So, why the renewed interest now? The explosive growth of AI workloads has forced data centers to rethink their architectures. At Data Center World 2025, analyst Jeremy Eliyahu-Ontiveros highlighted rack-scale architectures as a crucial solution for provisioning the massive infrastructure AI demands. AI workloads are unique. They require vast amounts of compute, memory, and often storage, all working seamlessly together. Rack-scale computing meets these needs by enabling hardware-level optimization within each rack. For example, 1 megawatt racks can house significantly more servers than traditional racks, ensuring AI applications have the resources they need to run smoothly. Additionally, rack designs that optimize data flow between servers and manage heat dissipation effectively help prevent bottlenecks and maintain high performance. This level of integration and optimization is difficult to achieve when provisioning individual servers separately. Rack-scale computing offers a more holistic approach, aligning infrastructure design with the specific demands of cutting-edge workloads. Of course, rack-scale computing isn't without its challenges. One major concern is scalability. If racks become the primary unit, expanding beyond the capacity of a single rack could be complicated. However, this issue is mitigated as data centers adopt higher capacity racks capable of supporting up to 1 megawatt of hardware. Looking ahead, as rack technology evolves, we can expect data center architectures to evolve alongside it. While individual servers will still play a role, since not every workload requires a dedicated rack, the most critical and resource-intensive applications are likely to operate at the rack scale. This shift raises some intriguing questions. Are we ready to rethink our data center strategies around racks instead of servers? Could this approach create new bottlenecks or complexities we haven't anticipated? And how will this impact the economics of data center operations? We'd love to hear your thoughts. Do you agree that rack-scale computing is the future? Or do you see potential pitfalls that could slow its adoption? Join the conversation and share your perspective below.